There are many applications in the world of finance, risk management, where we come across these extreme values or probably extreme events. Those events which can be categorized as very unlikely to occur, but if they occur, they are really creating they are really very costly to handle. They create a big financial damage, right? Those are the events which get categorized as the extreme events or the extreme values. So logically speaking, they can be classified as low frequency, high severity kind of events. So probably we can talk about a big market crash, stock prices falling drastically, or probably big financial institutions like Lehman Brothers collapse, which does not happen every day. It's a very rare event. Or probably any kind of financial crisis, right, like that of the 2008, which is not a very common stuff. So something like that, or any other big natural catastrophes like tsunamis and big hurricanes, cyclones, etc. All these, if I have to really understand their behaviors, because they are going to create big damage in case they are occurring. So the estimation for these things is a very important aspect. How do I estimate? One, the frequency for them. How do I estimate the severity for them? How do I estimate the total exposure which goes towards each of these events? Right? In general, it's very difficult because, first of all, the past data is very few past data points are present. And that too, because of that reason, I see that whatever the estimate that I am making, it would be an uncertain estimate itself. And that too, if I have to do an estimation, not just within the range, but even beyond the range. Let's say some earthquake has occurred and it has been between some unit X to some unit Y on the Richter scale. Let's say it has done some kind of damage. Now, if the earthquake severe than this comes, what would be the damage? It's very difficult for us to estimate. So, especially if the events have not occurred, or if I am expecting that the event can be more extreme than what has occurred in the past. Let's say a stock market crash, right? Stock price falling. Okay, let's say in a single day, if the stock price falls by 20%, what is going to be impacted? What could be the impact on the overall economy? I can't really visualize because we don't see any such kind of instances where the overall index has collapsed by more than this much percent. If these are the situations, very few data is there, and if at all I want to get into the estimate of those particular points much beyond, it becomes very difficult. And this is where it is purely based on the assumptions that are being made by the analysts and the statisticians. So lack of data is really being replenished by the various assumptions, and these assumptions always are subjected to question, right? So generally what happens in these kind of processes is people choose some distribution, let's say a log normal, or let's say a t, or there could be something else. There could be a Pareto distribution. Some kind of distribution is being selected, and the data is fitted to that, whatever the loss observation that we have seen, the data is fitted to that particular distribution. And in majority of the cases, what will happen is the central values will get fitted quite appropriately, but the extreme values will not get fitted properly, which means for the tails, this kind of mechanism does not work. So, which means whenever I am dealing with the extreme values, I need to have a completely different approach, right? So, dealing with low frequency, high severity events, I really require a different mechanism because these events are very rare. The data is not much present. I cannot combine these particular values with the regular, because regular ones can fit to any distribution, but these extreme ones may not be fitting in that particular distribution. And this is where the overall concept has come out, called as the extreme value theory. Just like a central limit theorem, which is more and more a base for fitting a majority of the distributions, where the central values really can fit the distribution quite comfortably. Extreme value theory is more targeted towards the extreme observations. So this has come out as a parallel thing to the central limit theorem, which is emerging out as a branch of applied statistics, which is trying to address all these extreme value problems. So it is more and more focused towards the extreme values. So which means compared to the central tendency attitude, you find that these models are completely different, because every statistic that is based on central tendency, it is governed by the central limit theorem. And the central limit theorem, we are saying that it will not be applicable to the extreme values. So we are going more and more with the extreme value based theorems. So which will talk about what kind of distributions should be fitted to our data, and what is the way we can estimate the parameters from the data for what kind of distribution. So they are more and more different, and it's a completely different study altogether. And in some cases it may so happen that the estimation of these parameters become more and more difficult. So whatever we are trying to understand as an extreme value theory, or understanding the characteristics of the extreme values, we really need to look at it as a different branch of statistics altogether, wherein different distributions will come into picture. As we move along, we will be seeing, we will encounter quite a different set of distributions. We will be talking about a Gumbel distribution. We will be talking about a Fréchet distribution. We will be talking about a Weibull distribution, which are all governed by the extreme value theory. So we can get into the understanding of the extreme value theory, which can simplify our process of estimating these extreme values that are encountered very frequently in the fields of risk management, insurance, finance, etc. All right.